All right, welcome to 2210 Podcast. And by request, I'm going to review how to balance chemical reactions using the matrix method. So a lot of times you may have been taught in high school sort of a guess and check approach, and that works for simple chemical reaction equations, but sometimes, particularly when you're dealing with physiological systems, the equations are quite a bit more complicated than that, so you need a more systematic approach. And so this is one chance you get to use some linear algebra, matrices, and so forth. So here's a problem from the Satterbeck book, or SMS book, problem 3.18e, and it says aerobic, which means that there's a reaction taking place with oxygen, growth of S. cerevisiae, which is a kind of yeast, on ethanol. So basically the yeast are eating ethanol. They're getting drunk. Party on. And the way you can actually sort of model this rather complicated series of physiological reactions taking place in the yeast as a single reaction, where you treat the yeast as if it's some kind of compound made of elements. And you can see it's a complicated formula. So it's one mole of yeast has 1 mole of carbon, 1.704 moles of hydrogen, and so forth. And you can see right here is the chemical reaction, which shows ethanol reacting with oxygen, because it's aerobic, ammonia. And here is the yeast is produced. So think of it as the yeast eating food and then producing more yeast. That's essentially what this is showing. It also mentions a respiratory quotient of 0.66, and that's the ratio of the moles of CO2 formed per mole of oxygen consumed. So the first thing you want to do is write the mole balances around the elements. And they have already actually put letters in front for the unknowns, and we're assuming that the first compound, the ethanol, has a stoichiometric coefficient of 1, and then we leave unknowns for the rest. So the way you would do this, you would write a balance equation for carbon, hydrogen, oxygen, and nitrogen. So carbon, and basically for every mole that is of an element that's part of a reactant, you treat as negative. And for every mole that is part of a product, you treat as positive, and you add them up, and they should sum to 0. All right, so for carbon, we're going to have negative 2 carbon elements as part of ethanol, as part of the reactant ethanol. And carbon does not appear anywhere else as a reactant, but it does appear as in the product of the yeast, and there's 1 mole times P. There's P moles of carbon per mole of yeast, and there are Q moles of carbon per mole of CO2. So all of that should equal 0. Okay, if we repeat that for hydrogen, we're going to have -6. Notice there's 5 hydrogens and then another hydrogen in the ethanol. And we're going to have -3 moles of hydrogen in ammonia, and then we're going to have hydrogen appears in the products of 1.704 P moles of hydrogen in yeast, and 2R in water, and that should all equal to 0. If we repeat that again for oxygen, we're going to have -1, -2A, plus 0.408 times P plus 2Q plus R, and that should sum up to 0. And finally, for nitrogen, we have negative B equals 0.149 P. And I'm sorry, that should be, whoa. You want to add those two. So negative B nitrogen in the reactant, moles of nitrogen in the reactants, and you have 0.149 P moles of nitrogen in the products. When you add those up, they should also equal to 0. So now we need to convert that. It's too complicated to solve through algebraic methods. Well, maybe it's not too complicated, but you're better off served using a little bit of matrix algebra, so to speak. So we're going to go ahead and convert this into a matrix on the next page. Okay, so there's also one other piece of information that I forgot to mention. Well, I mentioned it briefly about the respiratory quotient. We know the respiratory quotient, let's go back for a second. We know the respiratory quotient is 0.66. And so what that is saying, essentially, or actually I shouldn't bring this up, it's comparing Q to A. So what the respiratory quotient is saying, it's 0.66, which means that 0.66 is equal to Q, that's the number of moles of CO2 produced per mole of oxygen produced. So it's equal to Q over A. And another way of saying that is that 0.66A minus Q equals 0. So we're going to use that information as well to solve this problem. And the question is, how can I move this over to that previous page? Well, we're just going to have to remember that. 0.66A minus Q equals 0. It's 0.66A minus Q. Okay, so these are the equations we're going to use that we're going to solve simultaneously. So we need to get this in matrix form. So I kind of, write on the side here to keep track of what's happening. The different elements that I'm using to create this matrix, or the different equations, I guess you could think of. So I'm going to create a matrix. And we're going to multiply it by a matrix of the unknowns, which are A, B, over vectors, so say Q and R. And that's going to equal something. So, you look at C, you want to have this matrix multiplied by the vector of the unknowns, recreate this formula up here. So how can we do that? Well, we need 1 times P and 1 times Q. Everything else is 0. So we're going to have 0 times A. We're going to have 0 times B. We're going to have 1 times P and 1 times Q. And then a 0 right here. And all of that is going to equal to, we're going to take 2 to the other side of this equation. So all that is going to equal to 2. So that's the way you convert the mole balance equations into the matrix form. Let's do the rest. Hydrogen, we're going to have a 6 over here. Then we have a negative 3 times B, so it's 0, negative 3, 1.704 P, 0 times Q, and then 2 times R. Oxygen, we're going to have 1 on this side. And we're going to have negative 2 times A, 0 times P, 0.408 times P. I'm sorry, 0 times A. Boy, did I mess that up. Negative 2 times A, 0 times B, 0.408 times P, and we want 2 times Q and 1 times R. So that's the matrix version of oxygen balance. For nitrogen, it's going to equal to 0. And we have negative B, so it's 0 times A, negative 1 times B, 0.149 times P, and then the rest is 0. And then we need to convert the respiratory quotient equation into matrix form. So that's also going to equal to 0. We have 0.66 times A and negative 1 times Q. So we have 0, 0, negative 1, 0. All right, so that is our the matrix form of this problem. And now we just need to solve it. And in reality, on a test, I'm not going to ask you to solve it, but I will very likely ask you to complete this matrix form. But let's go ahead and show how we can solve this problem in Excel. So here, I've already put in the matrix. This, I don't know if I can write. Yes, I can. Okay, so this is the matrix that I just wrote on the previous page. So we have CHON and RQ. This represents C, CHON, and RQ, and this is the matrix. So we just enter those numbers into Excel, and then this is the other, the vector. If we go back to this previous one, that is going to be this guy. So we create that in Excel as well. So that's going to be these numbers right there. Now what I did here is, let's see if I can manipulate this. So if you look inside, I'm assuming you know a little bit about Excel. Underneath, in this, each square is you can put a formula. So the formula for this, so what we want to do to actually solve this matrix equation is to, let me go back. We need to reformulate this so that we're going to bring this matrix over here and multiply it times this vector. And so what you're going to end up with, and in order to do that, you have to do the inverse of that matrix. So basically, to solve for these unknowns, we have to multiply this vector times, and I'm not going to rewrite this entire matrix, but it's the inverse of the element balance matrix. Okay, so what you can do is in Excel, you can use the command equals M, standing for matrix, inverse, and then you select all of these squares. And then you have to remember to hit Control, Shift, Enter. And so what you do is you highlight the number of squares you need the solution that you put in. You then enter this command, and then you hit Control, Shift, Enter, and these numbers will pop up. Voila. Then the last step, and I'll demonstrate all this in a moment, but the next step is to use the command inverse, so M for matrix, inverse, and then you select it's the same process. You sort of highlight these cells, you then enter the command in inverse, you select the matrix, or am I messing this up? This is actually the multiplication of these two, so I'm not sure why that didn't show up. Okay, M multiply. So M for matrix multiplication. You highlight the cells where you want the answers to be. You then enter this command, multiply, and you select the two matrices you want to multiply by. And then again, you press Control, Shift, Enter, and then you'll get the answer, which is right here. All right, so let me see if I can reproduce this for you. I think we need to do a new page here. Okay, so I'm going to enter the matrix 0, 0, 1, 1, 0. Oops, 0, negative 3, 1.704. 0, 2, negative 2, 0.408, 2 and 1, 0, negative 1.149, 0, 0. And I think when I did it this time, I actually had the sign switched on this equation because they're equivalent. So I'll go ahead and put in what I did for the integrity video so it won't confuse you. So I have 0.66, this is the respiratory quotient equation, so it's 0.6600, negative 1, 0. We should get the same answer. And then the vector on the other side of this equation is 26100. Okay, so now, as I mentioned, the first thing we want to do is find the inverse matrix of this guy, and then multiply it by this guy, and we'll get the answer. So the way you do it is you want to select, we're going to need a 5 by 5 matrix here, so we select 5 by 5 cells, and then we say equals M inverse, and it even brings it up for you, that command, and then you select the array that you want to do the inverse of, so it's this guy. And we close that up with a parent at the end, and then you say Control, Shift, Enter. Boom, there is the inverse of that matrix. And actually, I did the inverse of the wrong matrix. So let's do this again. I can tell because it did not look right. So let's try this again. M inverse, and we want to do this matrix. And then we do Control, Shift, Enter, and there is our inverse of the matrix, and we want to multiply it by this matrix. So we want to multiply this matrix and this one, and that will give us the answer. And the answers will be A, B, P, Q, and R. So we want to select all the cells that we need an answer to be put into, and then we use the mmult function. And we select the two matrices we want to multiply by each other, put a comma between the two. No, that's not what I want. I want this guy. close it with a parent, and then you do Control-Shift-Enter again, and there is the answer. It's exactly the same as the one I got earlier. So basically the stoichiometric coefficient of A, which was for oxygen, is 2.9169. Stoichiometric coefficient for ammonia is 0.01115. Stoichiometric coefficient for yeast is 0.0748. Stoichiometric coefficient for carbon dioxide is 1.925, and the stoichiometric coefficient for water is 2.953. And it's advisable to check that everything balances out on your own time. Make sure that, for example, Q over A is 0.66. That's easy enough to figure out. Let's see. We could say equals Q divided by A, and indeed that's 0.66. That's a good sign that we did everything right. And that's how you balance complicated chemical reaction equations. Take care.